Data forms the fundamental building blocks of information. It represents raw facts, figures, or statistics. Information is derived from processed and organized data, providing context and meaning. In today's digital age, vast quantities of data are generated constantly. Without proper organization, this data remains chaotic and unusable. This is where databases become indispensable. A database is an organized collection of structured information. It is typically stored electronically in a computer system. Databases are designed to facilitate efficient storage, retrieval, and management of data. A database management system, or DBMS, is software that interacts with end users, applications, and the database itself. It provides a systematic way to define, create, query, update, and manage data. The DBMS acts as an interface between the user and the database. It ensures data consistency, integrity, and security. Without a DBMS, managing large datasets would be impractical and prone to errors. Key functions of a DBMS include data definition, data manipulation, and data control. It allows users to define the structure of the data and the relationships between different data elements. A DBMS comprises several essential components working in concert. The Data Definition Language, or DDL, is used to define the database schema. This includes creating, modifying, and deleting database objects. The Data Manipulation Language, or DML, enables users to interact with the data. This involves inserting new data, retrieving existing data, updating records, and deleting information. SQL is a common DML. The Data Control Language, or DCL, manages access permissions and controls. It ensures data security and integrity by defining who can perform specific operations on the database. Relational databases are the most common type. They organize data into tables, rows, and columns. Relationships between tables are established using primary and foreign keys. SQL, or Structured Query Language, is the standard language for managing relational databases. Examples include MySQL, PostgreSQL, and Oracle Database. They enforce strict schema definitions. NoSQL databases offer a flexible alternative to relational models. They are designed for handling large volumes of unstructured or semi-structured data. NoSQL databases prioritize scalability and availability. Examples of NoSQL databases include document databases, key-value stores, and graph databases. They are often used in big data applications and real-time web applications. A schema defines the logical structure of the entire database. It describes how the data is organized and the relationships among the data elements. The schema is essentially the blueprint of the database. Tables are the fundamental building blocks in relational databases. Each table represents a specific entity, such as customers or products. Tables consist of rows and columns. A row, also known as a record or tuple, represents a single entry in a table. For instance, in a customer table, one row would contain all information for a single customer. A column, or field, or attribute, represents a specific piece of data within a table. Examples include customer name, product price, or order date. Each column has a defined data type. A primary key is a unique identifier for each record in a table. It ensures that every row can be uniquely identified. Primary keys must contain unique values and cannot be null. A foreign key is a column or set of columns that refers to the primary key in another table. It establishes a link between two tables. Foreign keys are crucial for maintaining referential integrity. Data integrity refers to the accuracy, consistency, and reliability of data. It ensures that data remains valid and correct throughout its life cycle. Integrity constraints are rules that enforce data quality. Referential integrity ensures that relationships between tables remain consistent. For example, if a foreign key references a primary key, the referenced primary key must exist. Domain integrity ensures that all values in a column fall within a specified range or format. Entity integrity ensures that each row in a table is unique and has a primary key. Database security involves protecting the database from unauthorized access, use, disclosure, disruption, modification, or destruction. This includes user authentication, access control, and encryption. Access control mechanisms define permissions for users and roles. They specify what data users can view and what operations they can perform. This is vital for protecting sensitive information. The fundamental operations performed on data within a database are often summarized by the acronym CRUD. CRUD stands for Create, Read, Update, and Delete. Create operations involve adding new records to the database. This is typically done using an insert statement in SQL. New data is stored according to the defined schema. Read operations involve retrieving data from the database. This is performed using a select statement in SQL. Users can query specific data based on various criteria. Update operations modify existing records in the database. An update statement in SQL is used to change values in one or more columns of existing rows. Delete operations remove records from the database. A delete statement in SQL is used to remove one or more rows from a table. Careful use of delete is essential to prevent data loss. Concurrency control manages simultaneous access to the database by multiple users or applications. It ensures that concurrent transactions do not interfere with each other. Transactions are a sequence of operations performed as a single logical unit of work. They must adhere to ACID properties, atomicity, consistency, isolation, and durability. Atomicity ensures that a transaction is treated as a single, indivisible unit. Either all operations within the transaction are completed, or none are. If any part fails, the entire transaction is rolled back. Consistency ensures that a transaction brings the database from one valid state to another. It maintains all defined integrity constraints. Isolation ensures that concurrent transactions execute independently. The intermediate state of one transaction is not visible to other concurrent transactions. Durability guarantees that once a transaction is committed, its changes are permanent. Even in the event of system failure, the committed changes persist. Backup and recovery are critical aspects of database management. Backups involve creating copies of the database at regular intervals. These copies are stored securely. In the event of data loss, corruption, or system failure, the recovery process uses these backups. The database can be restored to a previous consistent state. Recovery strategies include full backups, incremental backups, and differential backups. A robust backup and recovery plan minimizes downtime and data loss. Database administrators, or DBAs, are responsible for the overall health and performance of a database system. Their duties are extensive and critical. DBAs manage database installation, configuration, and upgrades. They monitor database performance, troubleshoot issues, and optimize queries. They also implement and maintain database security measures. This includes managing user accounts, permissions, and auditing access. Furthermore, DBAs are responsible for planning and executing backup and recovery procedures. They ensure data availability and disaster recovery readiness. Effective database management is crucial for any organization. It ensures data accuracy, consistency, and reliability. This supports informed decision-making. Proper management enhances data security, protecting sensitive information from unauthorized access. It also ensures compliance with data privacy regulations. Efficient database management improves data accessibility and retrieval speeds. This leads to better application performance and user experience. Ultimately, robust database management systems are the backbone of modern information systems. They enable organizations to leverage their data assets effectively and efficiently.